Hello there. We're going to start our chapter 17. And we're going to be learning a lot of organic chemistry here in this chapter too. And especially a lot of about the reactions at the alpha carbon of a carbonyl compound. Okay, you will see beautiful reactions, beautiful chemistry that we can do, reactions, mechanisms, all that in this chapter. Okay. Now we know what is a carbonyl compound, and many of the carbonyl compounds have two sites of reactivity, and one of the site is this carbonyl carbon. A nucleophile come and attack the electropositive carbonyl carbon, and then you know what's going to happen. The pi bond opens up, and then the nucleophile is added onto the carbon. Now this sp2 carbon became sp3 carbon, right? So you have now tetrahedral carbon molecule. That is one site where we can react with the nucleophile. And then there is another site where if you use a base normally react with an acid. So if you add a base, we need to have an acidic hydrogen to react with. So a base can remove a proton, acidic proton from an alpha carbon. Remember the alpha carbon is the carbon next to the carbonyl compound. If this is your carbonyl compound, so this is going to be your alpha carbon. This is an alpha carbon. So the alpha carbon can have some hydrogens on it. So we call them as alpha hydrogen atoms. So this carbon has two alpha hydrogens. So when you add a base, so the base can take this acidic hydrogen. Okay, once the hydrogen is taken, the two electrons in the bond gives to the carbon. So then the carbon will become carbon ion, and then it forms the conjugate base. So this is the base. So base takes the hydrogen, so it will become conjugate acid of the base. Okay, so the two sites in a carbonyl compound that can react is one is addition to the carbonyl carbon, and then the other site is a base reacting with the alpha hydrogen of a carbonyl carbon compound. Okay. Now let's see why a base is able to remove that hydrogen. Hydrogens attack to sp3 carbon. So this is a sp3 carbon. Remember the sp3 carbons are when carbon has 4 electron groups attached to a carbon. For example, this is a tetrahedral carbon. This is hydrogen, hydrogen, hydrogen. And then you have a methyl group over here. So this is hybridization of that carbon is sp3. And if you consider acidity of the hydrogen attached to a sp3 carbon, the pKa is greater than 60. If you remember from your general chemistry, pKa measures the acidity of a compound. Normally that is for weak acids. pKa, we talk about pKa for weak acids. We do have some strong inorganic acids. Remember this strong acids? For example, sulfuric acid is a strong acid. Nitric acid is a strong acid. Hydrochloric acid is a strong acid. And then perchloric acid is a strong acid. And HBr is a strong acid. Hydrobromic acid. Hydrogen iodide is a strong acid. 1, 2, 3, 4, 5, 6. So all of these are strong inorganic acids. When they dissociate in water, they come 100% dissociate into ions. So we do not talk about pK values for these acids because they are strong. But we normally talk about pKa for weak acids. Okay, now in organic chemistry we have a lot of organic acids, and some of the organic acids are considered as carboxylic acids. Carboxylic acids have this functional group, and then you can have a different alkyl group. If R is H, that's a formic acid, CH3 acetic acid. So those are carboxylic acids. And also we can have other hydrogens, acidic hydrogens. Now this is an alkane. We don't normally consider this is an acid, but we can find out the pKa of that hydrogen. So we can compare the acidity of the hydrogens of of hydrogens on the carbon that is attached to sp3 carbon, and then what about the acidity of the other hydrogens on different carbons. Okay, so basically if you have a lower pKa, if you have a series of weak acids, lower the pKa, the stronger the acid. They are not never going to be strong as these acids, but if you are comparing the weak acids, lower the pKa, it has a higher acid strength. Okay, more strong the acid. And let's say you have a higher pKa. Higher pKa meaning that is a weak acid. I mean, they all are weak. Don't get me wrong. I'm comparing the weak acid strength. Okay. Now, this is pKa greater than 60. For example, let's say you have another acid that the pKa is 40. So, which one do you think is more stronger between these two weak acids? The pKa 40 would be more stronger. Okay. Okay. So pKa of a alkane hydrogen is greater than 60. Now let's look at the pKa of the hydrogen, alpha hydrogens. Remember, now you know what is alpha hydrogen. Whenever we talk about alpha hydrogen, it immediately comes to your head. It's the hydrogen attached to the alpha carbon, which is the carbon next to the carbonyl group. Okay, a hydrogen attached to an sp3 carbon adjacent to a carbonyl carbon has a much lower pKa value. Now this is also sp3 carbon. Okay, because it has two hydrogens, one alkyl group and a carbonyl group attached, 4 groups attached to it, and this carbon also sp3. Now the difference is this carbon is next to a carbonyl group that dramatically increases the acidity of this hydrogen. Let's see why. Okay, we'll talk about why it is so. You see the pKa of this alpha hydrogen is between 16 to 20, which is far lower compared to being pKa 60. Meaning these hydrogens are more acidic compared to the alkane hydrogen. Okay, and here's another one. In this one, this is an aldehyde and this is a ketone. Now this is also, you have a carbonyl group, but you don't call this as an aldehyde or a ketone. This functional group is ester. Now you can see in a ester, pKa is about 25, which is going to be less acidic compared to a alpha hydrogen of aldehyde or ketone, and there is a reason for that also. The difference is, you can see here you have a hydrogen and an alkyl group. Here you have a alkoxy group, oxygen and R, and we'll see why. Okay, the sp3 carbon adjacent to carbonyl carbon is called an alpha carbon. This is your alpha carbon adjacent to carbonyl carbon. Now if I ask you to identify the alpha carbons, this is an alpha carbon. This one also has an alpha carbon. And then if we expand the R group here, this can also have an alpha carbon right there. And this is alpha carbon, but this one does not have alpha carbon. Okay. A compound that contains a relatively acidic hydrogen bonded to sp3 carbon is also called a carbon acid. So we can call these as carbon acids. They are not in the same category like carboxylic acid, but we can call them as carbon acid. Okay. So these are some pK values of some carbon acids. So you can see here, this is an amide, it's about 30, and this is an ester, 25, and this is a ketone, 20, aldehyde 17, aldehyde. So if you compare the aldehyde, ketone, ester and amide, aldehyde hydrogen, alpha hydrogen would be the stronger acid. Okay, they all are weak acids, but between this is going to be the most stronger. And then we have a cyano group, cyanides. You have dicyano groups, and then you can have nitro groups, 2 nitro groups, 3.6. So when you have 2 nitro groups, so that's about 3.6. It's pretty acidic, 3.6, like acetic acid. Acetic acid pK is about 4.1 5, I believe. It's even acidic than acetic acid. And here's another one. Now you can see here there are 2 carbonyl groups. You see here this carbon is alpha to this carbonyl group as well as this carbonyl group. So it is 13.3. It's even more acidic compared to the aldehyde alpha hydrogen. Okay. And then this one, what do we have? We have 2 carbonyl groups and we have alpha hydrogen here. Here you have a ester group, whereas here you have just a methyl group. Okay, so this is a diester, but this is only one side of the ester. So this is going to be more acidic compared to this one. And then this guy over here has 2 methyl groups on the sides. So that's going to be even more acidic. And then when you have a hydrogen, that's 5.9. Now there is a reason for these different numbers of pK values. We'll see why they all having different pKa's. Okay, what is the reason, so you'll be able to figure that out too when we learn the trends and the reasons. The electrons left. Normally when you have a negative charge or when you have a positive charge, if there are other things that it can stabilize, or maybe what I mean by stabilize is whenever there is a charged species, it's always going to be unstable. Neutral would be the best. But if it is possible, if you have a highly negative charge, if there are groups in your molecule that it can make less negative, or if you can delocalize that negative charge, that would become more stable. Similarly, if you are going to generate a positive charge, positive means electron deficient. So if you have groups surrounding you that you can make it less positive. How do you make less positive? By giving electrons to it. Okay, just like your carbocation. Carbocation would be more stable when you have 3 methyl groups or a tertiary carbocation. Why? Because due to the hyperconjugation, the methyl groups can donate or push electrons towards the carbocation, decrease in the positivity. So likewise, once the hydrogen is left, always acid means a hydrogen donor. Once the hydrogen is left, you are left with a negative charge species that is highly electron rich. So if it is possible to lessen the electronegativity or the negative charge, then it would become more stable. The electrons left behind when a proton is removed from an sp3 carbon are localized on the carbon. Now this is an alkane. Okay, so one of the hydrogens is left. Let's say if you have CH3, CH, H, H. So a base comes, grab this hydrogen. Now the electrons in this bond gonna give to this carbon. So the carbon will end up having 2 hydrogens and a lone pair, then that generates a negative charge on the anion. Okay, now there is nothing that can stabilize that carbon ion. And we know the methyl groups are electron donating, so it would add more electron density towards carbon and become highly unstable. And we also called in this case it's a localized electrons. You cannot delocalize or spread that negative charge in the molecule. Okay, so that makes it less stable, meaning it has a pKa about greater than 60 pKa. It is less acidic. Okay, now let's look at what happens when a hydrogen is lost in an alpha carbon. How can it become more stable? The electrons left behind when a proton is removed from an alpha carbon are delocalized onto an oxygen. Now this is alpha carbon having a carbonyl group next to that. Now this is, we consider this as acidic hydrogen. So the base comes and grabs the hydrogen, gives its electron to this carbon. Now, in this molecule, since we have a carbon-oxygen double bond, this lone pair can be delocalized in the molecule. Instead of just staying on top of carbon, now it can spread out in the molecule. The lone pair gives its electron to form a double bond between the carbon-carbon, making a pi bond, having a double bond, and the carbon-oxygen pi bond breaks, and oxygen now bearing the negative charge. So it's not in one place. These two are resonance structures. So, and this can go back to this structure also. Okay. So, oxygen is more electronegative. The negative charge is better accommodate on oxygen than on carbon. So as a result, the negative charge that generate after removing the acidic hydrogen is more stable compared to an alkane carbon ion. Okay, and we call this process as delocalization. Okay, so the delocalization increases stability. The more stable the base, the stronger its conjugate acid. Okay, more stable the base, the stronger its conjugate acid. Oxygen is better able to accommodate the electrons than carbon. So this is the base that you generated. Now this is the acid. Okay. So we consider this as the acid. Acid is your carbonic acid, alpha carbon, carrying alpha hydrogen. And this we have written here is the conjugate base. Conjugate base. Now due to the resonance stabilization, resonance contribution, conjugate base is more stronger. So the more stable the base, so the base, conjugate base, the stronger its conjugate acid. So if this is the acid, this is your conjugate, this is the acid, this is your conjugate base, and this is the base, stronger the conjugate acid. Okay. Okay, a proton on alpha carbon of an aldehyde or a ketone is more acidic, pKa 16 to 20, than a proton on the alpha carbon of an ester. Remember, we talked about that earlier in this here in this chart, that the acid, aldehyde or a ketone, their pK values are 17 and 20, and then ester pK value is about 25. In general, aldehydes and ketone in the range 17 to 20 and ester 25. The difference is ketone has a hydrogen, aldehyde has an hydrogen, ketone has an alkyl group, and ester has oxygen and an ethyl group or any alkyl group. Now let's see what is the reason why they have different pK values. Esters are less acidic than aldehydes and ketones because delocalization of the electrons left behind when the proton is removed must compete with delocalization of the lone pair onto the carbonyl oxygen. Now let's say this is the ester. Okay. So this is the carbonyl group, and then you have the ester functional group. In an ester, once the hydrogen is removed from the alpha carbon, we would have this carbon ion. And this carbon ion can have resonance stabilization, forming a double bond and forming a single bond between carbon and oxygen like that. We have seen this with aldehydes and ketones also. Okay, so that is the delocalization of a lone pair on the carbon. And similar to that, in an ester group, we have this part also, alkoxy part, oxygen and alkyl group. This lone pair also forms a resonance structure with the carbonyl group. Lone pair gives its electron to this carbon-oxygen bond. Carbon-oxygen, this bond breaks up and we get this resonance structure. Delocalization of a lone pair on oxygen. So, because of that, this negative charge that we generate here is not fully available, completely available to make the resonance alone with only with carbonyl group. It is also need to compete with the oxygen in the ester functional group too. So as a result, the pKa of the ester alpha hydrogen is more, in the sense it has a higher pKa, meaning less acidic compared to ketone or the aldehyde. Okay. Okay. Here when you have diketone, we call this as acetyl acetone. So this is the acetone part and this is acetyl part. Acetyl acetone has two carbonyl groups. So the pKa is about 8.9, or you can call this as 2,4-pentadione, and this is a beta diketone. Okay. And on this one, here you have the same part, CH3CO, CH2CO, just like that. Instead of a methyl, now you have a alkoxy group, ethoxy group, and this is an ester. This is ethyl, this part you call this one, first ethyl, 1, 2, 3, 3-oxo, butyrate, 1, 2, 3, 4, butane, butyrate. That's the name. And also the common name is ethyl acetoacetate. Ethyl acetoacetate. It's also a beta keto ester. So this is your alpha carbon, alpha beta. In the beta position, you have a keto group, beta keto ester. Okay. The acidity of the alpha hydrogen increases in here because the electrons left behind can be delocalized onto two oxygens. In general, both of these have two carbonyl groups. And this is your alpha hydrogen, the highlighted in the yellow color, that is more acidic compared to your aldehyde or the ketone because it has two carbonyl groups. This one is more acidic compared to this. Again, this is an ester. Ester oxygen competes the resonance with the carbonyl group. So it's going to be less acidic compared to the beta keto diketone, a beta diketone. Okay. So this shows the diagram how the delocalization onto two oxygens. The previous structure that we have seen, this molecule over here, you can see how the delocalization. So this one, once you form the carbon ion, it can, okay, let's say this is the carbon ion, meaning that you have the hydrogen here, a base removed a hydrogen, you form this carbon ion. So it can delocalize onto this carbon. If it delocalize into this carbon and then the carbonyl group, you get this structure. But if the delocalization take place into the other one, you get this structure. Okay, so there are two resonance contributors. Ketoenol tautomers. Okay, we'll stop here and then we'll start the ketoenol tautomers in the next session.